Hi, I'm Justin Rutledge, and I'm here to describe the results of the data visualization assignment. So I've chosen a data set that contains weather data in London from 1979 until 2020. It's organized by day, so each row represents an individual day between those 41 years. It comes out to something like around 15,000 different rows, so it's quite the large data set. So I've loaded that into a pandas data frame, and then I've called head, tail, info, and describe to get some basic info on the data set. And as we can see from head here, we start at 1979, January 1st, and from tail we can see that we end on December 31st of 2020. Looking at some of the metadata, it's evident that these variables are measured in different ways, but we have cloud cover, sunshine, global radiation, temperature values, precipitation, pressure, and snow depth. Sunshine, for example, is measured in hours per day. So on January 1st, 1979, London got 7 hours of sunshine, where on January 2nd, there was 1.7 hours of sunshine, and on the 3rd, 0. And this corresponds to cloud cover to some degree, too. So some days, the sun just didn't shine. Global radiation is measured in watts per square meter, temperature is measured in degrees Celsius, precipitation in millimeters, pressure in pascals, and I don't remember what snow depth was, but it doesn't matter because we end up dropping that column anyways. Yep, and here's the reason why we drop snow depth, because it has only 13,900 rows, where every other column has somewhere over 15,300. So there's a lot of missing information in snow depth, so I've decided when we go to clean it up, we just drop it completely. I don't want to deal with the rows that don't have values there, and there's several nan values in some of the other rows as well, so we remove those completely by calling drop NA. That pandas function is really useful for that. And then I print the data set to just verify that everything's consistent now, and we'll scroll down real quick. And we see, yep, every single column now has the same number of rows. This is what we want. I then convert each of these columns into a NumPy array at least for the columns that I want to use to make visualizations. I've selected sunshine, global radiation, mean temperature, and precipitation, and then date as well to use as an index or to plot along the x-axis to show relationships over time. I load all of these into a single array, or into basically an array of arrays, to do a little bit of manipulation and transformation before we get into the visualizations. This includes converting the date from an integer value to a date time object for easier calling later, so I can just call, say, date.year. I do it by casting the integer into a string, slicing the string, and then casting back into an int and calling datetime.date to create a new datetime object for every entry in that array. Next, I find the averages of the sunshine and the mean temperature per year between 1979 and 2020. I wanted to illustrate in one of the visualizations, or two of them actually, how the temperature and sunshine correlate over time on an annual basis. It's easier to view than looking at it daily, since you kind of get seasons mixed in with the days. Taking an annual average is a better way of looking at the change over time for very long trends. And I do this by basically finding how many days are in each year, which are not 365 anymore because we removed several rows, so there might be 360 elements in some of these years that correspond to, say, 1980, whatever. So I find the number of elements that correspond to each year, and then I take the average of the sunshine for that year and the average of the mean temperature for that year and load them into their own arrays. All right, so now we get to our first visualization. I wanted to plot mean temperature and average sunshine between 1979 and 2020. I do this by using matplotlib and initializing the figure, and then calling plot to do a line chart. I load the year array for the x-axis, the mean temperature for the y-axis, and then label it. And then I also generate another line, but with the sunshine average array. Give the plot a title, label the x-axis, and this is cool. The xticks function will allow you to manipulate and send arguments to the tick values on one of the axes. And I chose to rotate it by 45 degrees to make it a little bit easier to read. Plot the y label, call plot.legend to generate a legend to show which line corresponds to which variable, and I put that in the upper left. You can send kind of free text arguments based on Matplotlib's I guess library. You can find out, upper left, upper right. There's some keywords that work. I chose upper left and then font size of 10 to kind of make it small enough to where it doesn't overlap with the lines in the line chart. And then I show the chart. So let's look at it. What do we see here? Well, first, it's worth noting that, yes, I've plotted degrees Celsius and hours per day on the same axis, the y-axis, which may seem kind of sloppy, but it allows it to be presented in the same chart in this way. But there's a lot of white space between the two. Either way, we can see there seems to be some kind of correlation here. When there's more sunlight, there's a higher temperature on average throughout the year. This is interesting. It seems kind of intuitive, but we can see that this might deviate kind of towards the later years here, but it's hard to tell with this chart. So what I did next was I decided to normalize the data using a min-max formula. So I basically took the minimum and maximum values in each of the arrays for the temperature average and the sunshine averages, and then essentially converted it to a number between 0 and 1 by taking the average of each of those values, subtracting the minimum, dividing it by the maximum minus the minimum. It's a pretty simple formula, but it will allow the data to be plotted between 0 and 1, and I can then rewrite the whole visualization for these, but instead of using the raw numbers for temperature and sunshine, I use the normalized values. Everything else is the same as the last chart, essentially, and we see them overlapped here and in a much clearer way. So I'll go back to the other chart. These two, kind of hard to look at the correlations directly. They're just spaced out far apart. There's some weird stuff going on over here. This is much easier to see the relationship between both of these variables, even though they're measured using different metrics, right? Celsius, degrees Celsius, and hours per day. This allows us to look at the relationships much easier. We see a very strong correlation for the first, 30 years, 20 to 30 years or so. But we see after 2005, there's evidence here that maybe there's something else that's having a greater influence on the mean temperature than sunshine, and it would be worth exploring some of the other variables that may be affecting that. And there's also some weird stuff going on here where there's a very strong dip, and it's just less correlated in the later years, and that's interesting to me. All right, the next chart, I decided to use a histogram. So just like before, we initialized the figure, but now instead of calling plt.plot to do a line chart, we do plt.hist to generate a histogram. We load the precipitation array. We determine the number of bins, which is basically the number of columns here. So I got 20 possible columns. Select the color of the columns and then the edge of those columns, which is black, to help kind of distinguish between them. Label the axes, give the plot a title, and then show it. It's a pretty simple few lines of code here. But what we see is that London doesn't get a lot of rain throughout the year. Over 12,000 days in these 41 years, and again, there's only 15,000 something days in all these years. The vast majority of the time, there's no rain. But it sometimes occasionally rains pretty hard. As we can see, even between 30 and 40 millimeters of rain, which is moderate to heavy rain in the area. All right, the last chart is a scatter plot. So again, like before, initialize the figure, but this time instead of calling histogram or plot, I call scatter. And I load two arrays here. One of them corresponds to the x-axis, the global radiation array, the other one to the y-axis, which is the mean temperature array. And note, this isn't the average values like before. This is the raw values for every single day between 1979 and 2020. Alpha here determines the transparency value of each of the points, which is helpful when there's a lot of overlap. You can see, for example, when the data is spread or more concentrated. Then choose the color. Label the axes, label the chart, and show the plot. One cool thing here, we can see a linear relationship between global radiation and mean temperature, where as the radiation increases, so does the temperature. But more interesting than that to me is that the range of possible temperature values narrows as radiation increases. So when there's almost no radiation, there's something like a 20-degree range for mean temperature. And then as radiation is about 400, Yeah, there are fewer data points here, but you can see the narrowing of that range to something more like 7 or 8. Because this is what, between 17 to 25? Yeah, there's a far narrower band of possible temperature values as radiation increases, which is a cool insight. And one thing is interesting is, I don't know, I would want to look into these outliers here. Why did the temperature spike for these points? Maybe something else was going on during those years, even though the radiation was low, that would have caused that. But that would just require a little extra investigation. There's a lot of cool things that we could continue to do with this data, but this really concludes the exposition for my part of this assignment. And we've reached about 10 minutes. Thank you very much. I hope you have a great day.